Swayam Prabha. Digital India. Educated India.
So, good morning all of you. We are continuing our derivations for similarity solution to different kinds of external boundary layer problems. So, we had looked at Falkner scan solutions and the corresponding heat transfer solution associated to Falkner scan velocity similarity solution in the last class, and we had taken some special cases for that where m equal to 0 indicates flat plate and m equal to 1 indicates stagnation flow. And in fact the stagnation flow is very useful because if you take for example the case of flow past a circular cylinder, and if you are looking at the stagnation region, you can convert the coordinates from whatever you have here to the cylindrical coordinate, and you can derive an expression for Nusselt number in the stagnation region of a circular cylinder. Okay, that is what we had seen last time. Okay, so apart from that, in fact the most generic case which we should have done is to consider a case of a boundary layer where you have transpiration at the walls. Okay, so the Falkner scan solutions that we did considered no slip at the wall and no transpiration. Okay, so in most of the cases where you employ what is called as boundary layer control. Okay, so you want to control the boundary layer because it is sometimes detrimental, sometimes it is beneficial. So accordingly you may want to control it to your requirement. So most of the times you may have to remove the reduce the boundary layer, or if you have a separation you want to reduce the separation. So all these things can be done if you actually not make it impervious but slightly porous. Okay, so that means you allow some kind of vertical velocity which could penetrate through the walls of this wedge. Okay, so this is basically your wedge angle beta pi. Okay, and your coordinate system is, this is your u velocity, v velocity, and this is your x and y. Alright, the limiting case of m equal to 0 leads to beta equal to 0, for which you have the flat plate case where you have transpiration from the walls of the plate. Alright. So we will consider the similarity solution for that today, and in fact this will be the most generic case, and you can also apply the case that we derived before where you say there is no vertical velocity, and that gives you the solution we derived in the last class. Okay, so for this particular case we will look at only the this flat plate, but it does not matter, we will apply the general Falkner scan solution applicable to many configurations. So the similarity equation that we derived in the last class is still valid because the boundary condition is not going to change the similarity equation, right. So what we did was simply substitute for u velocity, v velocity, and also all the gradients, derivatives, everything in terms of the similarity variables. So that is still going to remain the same, and therefore the similarity equation that we derived, similarity equation for Falkner scan solution is still going to be valid. So I am going to write it down. Okay, so let us call this as equation number 1. This is your Falkner scan similarity equation. Okay, so the equation is the same, the only thing that you need to modify is what? The boundary condition. Okay, so earlier we put the boundary condition that since u equal to 0, so your df by d eta at eta equal to 0. So this should be equal to 0, right, and at eta going to infinity this should be equal to 1. And apart from this, what was the other boundary condition that we gave, the Falkner-Scan case? I am just talking only about the flow right now. F equal to 0. Okay. So what does that indicated? V equal to 0. So this corresponded to the boundary condition V equal to 0, right? Okay. So in fact, if you had look at the expression for the velocity V, maybe I can just write it down for your benefit. We go back to, yeah, so that is basically V by u infinity is equal to half square root of nu by u infinity into x into eta df by d eta minus f. So this was the expression for V. So at the wall we have already mentioned that df by d eta equal to 0. So in order to satisfy the condition no slip V equal to 0, this also has to be 0, right. So this corresponds to the fact that V equal to 0. Now in this case we cannot do that because you have some small velocity, transpiration velocity, okay, which has to be specifically accounted for in the boundary condition. So therefore the solution for the equation has to be different, because the equation, although it is the same, the boundary condition is now different. Okay. So this is how you are including the effect of transpiration into the Falkner-Scan solution. So for this let us look at what is the appropriate boundary condition. So now let us write down the expression for V. Let us derive it from first principles, because now your u infinity is a function of x. Okay. So let us derive from first principles and see how it looks. So this is nothing but d by dx, the stream function in terms of the similarity variable can be written as u infinity nu x into f of eta, right. So all of you agree. So we had derived this for the Blasius case, so the same thing is valid, only thing now your u infinity is a function of x. Okay. So we are looking at solution to problems where u infinity varies as cx power m. Okay. So if you now differentiate it, let me also do that once myself, minus d by dx of, we can take f out, differentiate by, plus you have square root of u infinity nu x into df by d eta. In fact this will be d total derivative here, df by d eta into d eta by dx. Okay. So you can substitute for u infinity in terms of cx power m. So this will be m plus 1 inside the square root. Okay. So this also can be written as c nu x power m plus 1, right. So now how will you differentiate it? So you have minus f of eta, so d by dx of this square root of c nu, this is a constant, so this is m plus 1 by 2, right, into x to the power m plus 1 by 2 minus 1, alright. So then plus you have square root of c nu x power m plus 1, so you can also write this as square root of c nu into x power m plus 1 by 2 into df by d eta into d eta by dx. So now again we have to differentiate eta with respect to x, and we know our eta is nothing but y square root of u infinity by mu x. Okay, now again u infinity you have to write in terms of x, so this will be y square root of c by nu, so x power m minus 1 half. Okay, so x m minus 1 by 2. So when I say d eta by dx, so this will be m minus 1 by 2 into y square root of c by nu into x power m minus 1 by 2 minus 1. Okay, so this is what I get for d eta by dx, which I can substitute here. Okay, so I can just write it as d eta by dx. In the next step I am going to substitute and simplify. So this will be minus f of eta m plus 1 by 2 into x power m minus 1 by 2 into square root of c nu plus minus c into so what I am going to do is, now my d eta by dx has square root of c by nu, square root of nu and nu cancels, square root of c into square root of c is c, so therefore I get a c, and x power m minus 1 by 2 minus 1 into x power m plus 1 by 2. Okay, so what does it give? X power m minus 1. Okay, so therefore I will have x power m minus 1 into, I have m minus 1 by 2 into y, so I have y into m minus 1 by 2 into df by d eta. Okay, so finally this is what I get for v velocity. In fact, you need to know this when we derive the Falkner-Scan solution. And I think I omitted these steps because I want you to do that yourself. Now I have done that. You can substitute then for u and v into the boundary layer equations, and finally you cancel off all the common terms, you will end up with this equation. Okay, I am doing the same thing now because we are more interested in the v velocity at the wall, therefore I am doing this specifically now. So now at the wall your y equal to 0, right? So what happens, this entire term disappears. Okay, so therefore at y equal to 0, let us call this as let us call the vertical velocity for transpiration as some v small s. Okay, so therefore this will be equal to v small s, which will be minus f of 0 eta equal to 0 m plus 1 by 2 x power m minus 1 by 2 square root of c nu. Okay, so this is the expression for the transpiration velocity at the wall. Now what can you say about the variation of the transpiration velocity with respect to x? Now the transpiration velocity need not be a constant. Okay, so see, from here it says that it can vary with x. Okay, but to find a similarity solution, this particular boundary condition gives us a constraint for the variation of Vs. So can you guess what should be the variation of Vs, how it should vary? Can it vary in any arbitrary manner, say some x power n? Suppose it varies as x power m, let us say. Okay, so what will be the expression for f of 0? So you have something to the power dependence on x, right. So once you have dependence on x, is that a similarity solution? So it will not be a similarity solution, right. So it will not lead to, if you have a boundary condition in terms of f which is a function of x, so it does not give a similarity solution. So therefore in order to make sure your f is a constant, so only a constant value of f can lead to a similarity solution, it should not vary with x or y, okay. So for that case, so your Vs has to vary as x power m minus 1, that is the only possible way, correct. Only then your f at y eta equal to 0 can be a constant, okay. So from this it clearly demonstrates that you can have a similarity solution to the Faulkner-Scan problem with transpiration only if your velocity varies as x power m minus 1 by 2. So only then the similarity solution is possible. Okay, only then your f of naught is a constant. For a given value of m, then your f of naught will become a constant. Okay, so now putting this condition, we can write in terms of the boundary condition for f at eta equal to 0. Let us call this as equation number 2. So therefore from 2 you can, in fact you can also expand one step further, you can write your c in terms of u infinity by x power m. So you can write c is equal to, because that is your condition here for the free stream, and you can substitute into 2. So that will give you Vs as minus m plus 1 by 2 into f of 0 into, so if you multiply and divide by u infinity, I think you should be getting something like u infinity of x by square root of u infinity into x by nu, okay. You please check if this is correct, u infinity by x power m. So this is basically square root of u infinity, that is correct, yeah, x power m, I think that will give you square x power minus half, yeah, right. So that should lead to this particular form, right. So this is nothing but square root of u infinity by square root of x by nu, okay. So if you substitute this into c, there you will be ending up. So why I am doing this, I am just rewriting in terms of Reynolds number, that is all, okay. So now from here you will get your f of 0 as minus 2 by m plus 1, okay, into Vs by u infinity of x. Now this is nothing but what, Reynolds number to the power half, so that will go to the numerator. So this is your boundary condition now, okay. So you have put a condition on the variation of your transpiration velocity with your x, it has to vary this way for a given value of m, okay. So when do you say that you have a similarity solution? So you have of course reduced your partial differential equation in terms of the similarity variable eta, you do not have any x and y here, okay. Also the boundary condition should not have any terms in terms of x and y, okay. Now when you write down the boundary condition for f of 0, now you see it is a function of some x, okay. If you want to make this independent of x, and make it a constant, you have to make sure that your transpiration velocity varies exactly by the same factor. Okay, so this is the constraint that is required in order to get a similarity solution for this particular boundary condition. So this has to satisfy this particular constraint. Okay, for a given value of m, your v has to vary according to along x as this particular relation. Okay, only then you get the similarity solution, because once you rewrite now, what you are saying is this entire term is now what? Constant. Okay, if your Vs varies that way, your f naught has to be constant. So this entire term has to be some ratio which is constant or fixed. Okay, this ratio is called the blowing ratio. Okay, you can give maybe some other notation to that. I don't want to give anything. I just want to describe Vs by u infinity into Rex basically is nothing but your blowing ratio, which means that is something like ratio of V by x power m minus 1 by 2, which is nothing but some constant. Okay, so that blowing ratio is specified for a particular problem. You specify that your blowing ratio is, say, some value something like 0.5 or minus 0.5 depending on whether you blow or whether you are sucking the flow, and based on that, for a given value of m, there is a constant value of f naught which gives you a similarity solution. Okay, so you solve the same similarity equation. Okay, your other boundary conditions remain the same. So what is your other boundary condition? Your f dash of 0 equal to 0, okay, and your f dash at infinity equal to 1. So these two boundary conditions are same. The only boundary condition which is now slightly different is this, and this is also not so different. Earlier this was 0. Okay, so for the case where m equal to 0, okay, so this for this particular case Vs can vary only as x power minus half. Okay, so in that limiting case, you can get f of 0 as 0. Okay, you can probably just check. So when m equal to 0, Vs varies as x power minus half. Okay, so yeah, and if you don't have any transpiration velocity, of course this will be 0. So therefore if your Vs is equal to 0, so this gives your f of 0 as exactly 0. Otherwise this is your corresponding expression. So you know what is the blowing ratio, depending on that you calculate the constant value of f naught. Okay, so the same procedure that you used to solve the other similarity equation, the shooting method, exactly the same way you do it. Okay, only thing is now you have a value of f of 0 which is some constant value instead of 0. Okay, so that is the only difference. Okay, if you want me to write down the summarize the shooting method equations, probably I will do that again. So now you say your f prime equal to some g prime equal to h, and therefore what will be the corresponding equation? This will be h prime is equal to minus of m plus 1 by 2 into f into h plus minus m into 1 minus what is df by d eta g square is equal to, okay, so this is your set of ODEs, first order ODEs that you have reduced from the given third order ODE, and the corresponding boundary condition. So your earlier it was f of 0 equal to 0, now f of 0 is equal to minus 2 by m plus 1 into blowing ratio. Okay, so this entire thing, let me use the notation BR. It could be some constant value, either positive or negative. Okay, so therefore for a given value of m, this is some constant. What is the other boundary condition? G of 0 will be 0 because G of 0 is f prime. Okay, so the other boundary condition is what? G at large value of eta, say eta going to 10, eta equal to 10 for example, this will be equal to 1. Okay, so you don't know the value of h, so once again you can guess the value of h of 0, okay, such that finally this condition is satisfied, right. So you know the value of f of 0, g of 0, you don't know value of h of 0, so you guess h of 0 iteratively. I have given you the algorithm, Newton's algorithm, such that you get better and better guesses for h, so that it satisfies this particular equation ultimately. Okay, so the same exactly whatever the Newton's procedure and shooting technique that you use to solve is perfectly applicable, only that your f of 0 is not 0 anymore, it is just a constant value, that is all. And for if you write a program, it does not matter for the program, only you have to give some constant value there. Okay, so you do not have great effort in. So this is the most generic solution. So you have this Faulkner scan solution, you have generic boundary conditions. For the case where your blowing ratio is 0, this becomes a no transpiration case, and for different values of m you get different configurations. Okay, so let me just summarize and write down the corresponding values of the curvature at the wall, that is f double prime, that is basically nothing but h of 0 for different values of blowing ratio, okay, for a flat plate case. So let me erase all of this. So now since I have so many parameters, now I have to fix some of the parameters. I am saying for m equal to 0, that is for flat plate, okay. Now this is a flow problem, so I do not have to fix any other number like Prandtl number or anything like that. So for this particular case I have to check what is my f double prime of 0 for different values of blowing ratio, which is nothing but Vs by u infinity Rex power half. Okay, if I tabulate it, in fact I have given you one problem in the tutorial, second tutorial, to do this. I have asked you to vary the blowing ratios to different values and check what is the corresponding value of f double prime at 0. Because why do you need f double prime 0? Because this is directly related to the skin friction coefficient or wall shear stress. Okay, similarly your theta prime of 0 is directly related to your heat transfer coefficient. So these are finally what you require in order to calculate your heat transfer coefficient and skin friction. Okay, for the value of minus 2.5, so these minus values actually indicate suction, right? So negative velocities, and 0 indicates that. Okay, now you tell me what should be the value for blowing ratio of 0, 0.332, okay, which we have already derived from Blasch's solution. So for 0.250, then you have 0.5, 0.585, okay, this is like 2.59. so you can see the curvature increases with suction and actually decreases with blowing. 0.945, 0.523, 0.165, 0.036, and finally it becomes 0. Okay. So what do you think is happening here? It becomes 0 for a blowing ratio of 0.585. Flow is separating there. Okay. At the separation, your du by dy is exactly 0, your f double prime is also exactly 0 there. Okay. So once it separates, there is no point in going beyond a blowing ratio of 0.585, that is why it is limited to that value. So boundary layer theory is not applicable to that. Okay. So this is all blowing, and the above one is suction. In fact, the curvature you can see increases because you are trying to, if you even have a separation, if you suck it, the separation gets minimized and you will have a more of a boundary layer flow. Okay. So we will now quickly go to the heat transfer problem. What do you think will happen to the heat transfer similarity solution? How about the similarity equation for heat transfer, will it change? From what we derived for Falkner-Scan solution. Okay, let me also write the fact that the skin friction coefficient is nothing but twice of f double prime of 0 by square root of Reynolds number. Okay, so for the case of m equal to 0, this becomes 0.664 by square root of Reynolds number, which we derived for the flat plate case. So coming to the heat transfer problem. Okay, was this covered under incompressible flows, transpiration? How about the heat transfer, advanced heat and mass transfer? Okay, you are asked to derive the similarity solution or something. Huh?
We are asked to derive integral solution.
Integral solution.
Yes, sir.
Okay. Yeah, integral solutions are anyway what we are going to do from maybe tomorrow onwards. Okay, we will try to complete the similarity solution in the next 1 or 2 classes. Coming to the heat transfer, so what should be the equation for similarity equation for heat transfer? Exactly identical to what we derived, right? No change, and boundary conditions also now don't change. We assume that you have a constant wall temperature, okay, and u infinity, t infinity, and once it comes here, this becomes u infinity of x and still t infinity. Okay. So whatever equation that we derived last time for Falkner-Scan, the same thing remains, and the boundary condition also the same. Okay, so the only thing this solution changes because the value of f changes now, okay, and that is used to calculate the non-dimensional temperature. Okay, as such the equations and boundary conditions are the same, but the solution will be a different solution. So therefore you are more interested in the Nusselt number. If you are looking at Nusselt number, this is d theta by d eta at eta equal to 0 into Rex power half. This is what we derived finally. So this is how the Nusselt number is related to the non-dimensional temperature gradient. Okay, so all we are interested is theta prime at 0. So let us tabulate okay, for some more. I think this is coming from you, from one of your textbooks. So Prandtl number equal to 0.7 and also m equal to 0. So for this case your blowing ratio versus your d theta by d eta equal to 0. So 0, this is only for blowing, not for suction, 0.375, 0.5. So once again, just like your velocity gradient keeps reducing, your temperature gradient also has to keep reducing. Okay, so 0.292 0.166, 0.107, 0.0517. Okay, so this, with this information you can plug in for the say Prandtl number of 0.7, for a blowing ratio of this you can plug in this value, and that is the relationship of Nusselt number with respect to Reynolds number. Alright, so the same thing applies, only thing you have to use the value of blowing ratio, calculate different values of f, and therefore solve the equation again by shooting method, and from that you get your non-dimensional temperature gradient at the wall. Okay, the same procedure whatever you did earlier, same shooting technique applies. Okay, so any questions so far? Okay, so one more last topic we will see for similarity solution before we move on to integral methods. So this is for, so far in the energy equation we have not accounted the viscous dissipation effects, we have neglected them safely because we said we are looking for low speed flows. What if the viscous dissipation effects are also considered? Do we find a similarity solution for that case? Yes. Okay, even for this Falkner-Scan solution, if you include the viscous dissipation effects into the energy equation, we do indeed find a similarity solution. Okay, so let us not do it for the general case, let us do it for a flat plate case, and I just want to tell you that the same thing can be done for the case of Falkner-Scan solutions also, because it is only the energy equation which is affected. Okay, the flow remains the same. Alright, so let us move on to that topic where we consider viscous dissipation effects. Any questions on this so far?
Why will the momentum, like why will the flow remain the same? That should also vary
because we are not considering variable properties. Okay, we are assuming that constant property assumption is still valid. If your properties are function of temperature, then yes, then you do not have similarity solution in that case. Okay, in all these cases we are assuming that the temperature, the flow field, they are decoupled. Therefore, you first solve for the flow and that is used into the temperature equation. Alright, so it is a constant property assumption. Okay, so of course most of the flows where you have strong heat transfer at high temperatures and strong temperature gradients, you will have considerable variation. Okay, so that is the assumption that we are using in all of these. So let us look at some of the assumptions before we so thermal boundary layer flow over a flat plate. Although I am doing this for flat plate, the same thing is applied to even wedge flows. Okay, so when I say high speed here, I am just indicating that the ratio of Eckert number by Reynolds number is very important, and therefore the viscous dissipation has to be considered. So to write down the boundary layer equations, in the case of flat plate anyway I am not going to consider the pressure gradient. Okay, so these are your complete equations for flat plate where you do not consider pressure gradient term. Now we have also included the viscous dissipation. If you non-dimensionalize this, you will get this as the ratio of Eckert number by Reynolds number, where how is your Eckert number defined? Do you remember? U infinity square by Cp say T wall minus T infinity. Okay. So now this is subject to the boundary conditions that at y equal to 0 your U and V are 0, and for temperature you can say you can either have a constant wall temperature or you can also have an adiabatic temperature, adiabatic wall. I mean you are not allowing any heat transfer to take place at the wall, but internally the temperature will vary because of the viscous dissipation. You are understanding the fact? So your viscous dissipation is an internal generation of heat. Okay, you do not need to transfer heat externally with an internal generator, because your kinetic energy is converted into is dissipated into heat at the viscous level, at the molecular level. So that is changing the temperature locally. Okay, because this gradient of course varies inside, so therefore there is a local variation of temperature. So even if you maintain an adiabatic wall, you can get a temperature profile if you have viscous dissipation. So therefore for high speed flows considerable effects can be observed, where your temperature will vary from the free stream temperature because of viscous dissipation itself. Okay, so you can also have heat transfer case even if you do not have any heat transfer through the wall. Okay, so therefore you can also maintain a boundary condition that your dt by dy is 0. So in either of these cases you can solve for heat transfer. Okay, so and similarly at y going to infinity, your u equal to u infinity and your t becomes t infinity, and same thing at x is equal to 0. Okay, so these are your governing equations. Now you can use the same boundary layer similarity expressions and substitute for u, v all the gradients. I am not going to do that. Okay, so if you substitute that, you will get a final similarity expression which is something like so if you substitute and you clean up all the unnecessary terms, this is the final similarity expression solution equation for temperature, because the flow still is the same as the flat plate Blasius solution. Okay, so only the energy equation will be changing a little bit, so and that change will be a term which comes on the right hand side. Because of the viscous dissipation, you have now this additional term which comes into the similarity equation, right? Now why do I write this in terms of dimensional temperatures? Why am I not directly non-dimensionalizing here? This is because now you have in fact two temperatures with which you can non-dimensionalize. Okay, so you can have your free stream temperature T infinity, and you have what is called as the adiabatic wall temperature. Okay, so this is the wall temperature if you maintain an adiabatic boundary condition at the wall. As I said, you can have a heat transfer due to internal generation, due to internal viscous dissipation, and that will result in a wall temperature which corresponds to the case of no external heat transfer. Okay, and that is defined as the adiabatic wall temperature. Okay, so if you do not have any heat transfer, instead of using instead of using something like a free stream temperature, you can also use adiabatic wall temperature. So therefore you have too many temperatures here, and we do not know which one we have to use to scale or non-dimensionalize the temperature. Therefore we will split this problem into two sub problems, one in which we have T equal to T wall, for which we have already derived the similarity equation, the Polhausen's equation. Okay, the other problem where you have only adiabatic boundary condition. Okay, so finally if you look at the energy equation, since this is quasi linear and also the boundary conditions are linear, we can safely say that the solution can be also split into two solutions and we can combine them in some linear fashion. Okay, so one solution will be for the Paulhausen solution, the other where you have adiabatic temperature including the viscous dissipation, adiabatic condition with the viscous. So these two solutions can be then linearly combined and we can construct the final solution to this particular problem. Okay, so just to give you an idea how the temperature profile looks before we wrap up, if you plot your temperature in the x axis and so somewhere, so at y going to infinity your temperature will be your free stream temperature. Okay, so there somewhere at y going to infinity that will be the free stream value, and from there if you maintain, as I said, the problem number 1 is solving this without the viscous dissipation with constant wall temperature, that is the Paulhausen solution. How will you get your temperature profile? It will be like this, right? This is the variation for case 1 or problem 1. This is nothing but your Paulhausen solution. Okay, now if you do case B, that is you apply a adiabatic condition at the wall but you include the viscous dissipation term, how does your temperature profile will look is something like this. Okay, and the temperature value that you see here is the highest, that is nothing but your adiabatic wall temperature, and the condition that the flux has to be 0 make sure that this becomes normal, right, at the boundary. Okay, now if you have a combined case, the case that we are looking here has both the solutions which you can linearly combine. Okay, you have a constant wall temperature but you also have a viscous dissipation, so then it has to forcibly return to this wall temperature which is a boundary condition, but it will go through a process something like this, like this. Okay, so this is your case B. Okay, this is your adiabatic wall including viscous dissipation. Now what I have drawn here, okay, this line, this profile is for case A plus case B, which is actually the solution, let us say, to equation number 1. With the boundary condition that you can have either a constant wall temperature or the adiabatic temperature. So finally, because of the viscous dissipation, you force the temperature at the wall to T wall, but the viscous dissipation effect will deviate the profile from the Paulhausen profile. Okay, so as I said, that is the clue to solving this problem, which we will do tomorrow. We will split the solution into two parts. Case A will be the Paulhausen, which we already did. Case B will be the adiabatic case with the viscous dissipation, which we will do, and for each of this there is a way of to non-dimensionalize theta. Okay, so in this case we non-dimensionalize with T infinity, T minus T infinity by T wall minus T infinity. In the other case we cannot use T wall because there is no wall temperature boundary condition there, so we have to use a different temperature scale which we will define. Okay, and finally we will express the final solution in terms of the linear combination of those two solutions. Okay, so we will stop here today.